welcome to the Explainer. Today, we're going to unlock a mathematical cheat code. It's for a problem that looks pretty simple, but trust me, it can quickly turn into a total nightmare. We're talking about raising complex numbers to a high power.
Okay, so first, let's really get a feel for why we even need a shortcut. I'm going to start us off with a challenge. And, on the surface, it looks pretty straightforward, but it quickly becomes this massive headache if you try to tackle it the hard way.
So imagine someone asks you to solve this. That little I there is, of course, the imaginary unit, the square root of -1. Now, your first instinct is probably just multiply it out 10 times, right? But let's see what kind of a mess that actually makes. So you'd have to multiply 1 plus I by itself. Okay, that gets you 2I. Then you take that result and multiply it by 1 plus I again, and then again and again, like 8 more times. I mean, this brute force method is just so tedious, it takes forever. And it is so easy to make one tiny little mistake that completely throws your whole answer off. And yeah, thankfully, there is a better way. But to get there, we have to stop thinking about this problem as just a multiplication marathon. We've got to start looking at it from a completely different angle. And that brings us to de Moivre's elegant shortcut. See, the secret isn't about multiplying faster. No, it's about changing our whole perspective. It's about using a much, much more powerful way to write these numbers in the first place. Okay, so complex numbers can actually be written in 3 main forms. Now, we're all used to the rectangular form, right? The a plus ib, and that's great for things like adding and subtracting. But the real magic, especially for our problem, is in the polar and exponential forms. These describe a number by its distance from the origin, that's r, and its angle, which we call theta. And this is it. This is de Moivre's theorem. It's literally the mathematical cheat code we've been looking for. All it says is this: to raise a complex number to a power, you just raise its distance r to that power, and then you multiply its angle theta by that power. That's it. It turns that nightmare of repeated multiplication into 2 super simple calculations. And check this out. Here's the link between those polar and exponential forms. It's called Euler's formula, and it shows that the whole cos theta plus I sine theta part is actually identical to e to the I theta. I mean, how cool is that? It reveals this incredibly deep and beautiful connection between exponents, trig functions, and imaginary numbers. And it gives us an even more compact way to write everything. A special case of this formula, when theta is exactly pi, gives us what's called Euler's identity. People often call it the most beautiful equation in all of mathematics. And you can see why. It so elegantly links the 5 most fundamental constants in the universe, 0, 1, e, pi, and I, all in one simple, perfect statement.
But wait, there's more. De Moivre's theorem isn't just for calculating these huge powers. It can also work in reverse. And when it does, it lets us do something that seems kind of impossible at first, finding all the hidden roots of a number. Now, this might sound like a trick question. What are all the cube roots of 1? Well, we all know that 1 cubed is 1, so duh, one of the roots is obviously 1. But hang on. The fundamental theorem of algebra tells us that a cubic equation should have 3 solutions. So where are the other 2?
Well, the process uses a version of de Moivre's theorem that's specifically for roots. First up, we write the number 1 in its polar form. Simple enough. Then we apply this root formula you see here, and what we do is plug in different whole numbers for k to find each separate root. Since we're looking for a cube root, we're going to test k equals 0, k equals 1, and k equals 2 to find our 3 solutions. Okay, so when we plug in k equals 0, the whole formula simplifies right down, and we get the answer we already knew, 1. Yep, no surprises there. But when we set k equal to 1, this is where something amazing happens. The formula spits out a hidden complex root. Now, this number doesn't look anything like 1, but I promise you, if you were to cube it, the result is exactly 1. And then for k equals 2, we find the final piece of the puzzle. It's another complex number that, you guessed it, also cubes to 1. So there you have it, all 3 solutions. And what's really cool is that we haven't just found numbers, we've found points. If you actually plot these 3 roots on the complex plane, they form a perfect, beautiful, equilateral triangle right at the origin. It just goes to show you the deep geometric nature that's hidden inside these numbers. Okay, so why does any of this matter outside of a math class, right? It turns out this really abstract way of thinking is actually the backbone of modern technology. Specifically, it's absolutely fundamental to electrical engineering. We're talking about the analysis of alternating current, AC, the very electricity that's coming out of your wall sockets right now. See, with direct current, or DC, think of a battery, the voltage is constant and the math is pretty simple. But with AC, the voltage and current are constantly changing. They're oscillating back and forth like waves. And here's the crucial part. Those waves can get out of sync with each other. That's a concept we call phase. So, to handle all this complexity, engineers had this absolutely brilliant idea. They decided to use complex numbers to represent these AC quantities. The magnitude, or our R from before, represents the size of the voltage or current, and the angle, our theta, represents its phase. Oh, and by the way, in electronics, they usually use J instead of I, just so it doesn't get confused with the symbol for current. And this is so powerful because it lets them treat all the different kinds of opposition to current. You've got your basic resistance, plus this other stuff from inductors and capacitors called reactance. It lets him treat all of that as parts of a single complex number. They call it impedance. The real part is the resistance, and the imaginary part, that's the reactance. All right, so let's bring this all full circle. What started out as a tricky math problem actually ends up being a fundamental tool for building the entire modern world. And, just like in our original math problem, engineers are constantly switching between these forms depending on what they're doing. If they need to, say, add up voltages in a series circuit, they'll use the rectangular form. But if they need to multiply or divide to figure out power or impedance in a parallel circuit, boom, they switch right over to the polar form. It's all about using the right tool, the right perspective for the job. So in the end, the true power here isn't just the formula itself. It's the bigger, more profound idea that it represents. It's the idea that a simple shift in how you look at something can transform a problem from being nearly impossible to elegantly simple. And that's true whether you're working in pure mathematics or designing the very circuits that power all of our lives.